So we're going to start Unit 9, which is actually two kind of, I don't know, smaller units in one, thermodynamics and electrochemistry, although they are, of course, related. The thermodynamics part of it, we've kind of talked about most of this already in chemistry, in our honors chemistry. The first topic is just an introduction to entropy, the concept. So not really looking at numbers and doing any math with it, but just understanding what entropy is. So entropy gets the symbol S, and it is, you can say it a bunch of different ways, the disorder, the randomness, or the dispersal of matter in a system. And so one way to look at it is if you look at water, right? So you have solid ice would have a very low entropy. And you can see there in the explanation, the molecules are only able to sort of vibrate back and forth in place. And as soon as you raise the temperature up to melting, all of a sudden the entropy just goes really, goes through the roof, goes a lot higher, because now they're able to not only vibrate, but also rotate and flow past one another. And then as we get to vapor, as a gas, those water molecules are going to have a huge amount of entropy. They're still able to rotate, vibrate, and translation, which again just means flowing. But now they have even more space to occupy, which allows entropy to increase as well. So if we just sort of look qualitatively at entropy, the first thing we need to understand is that physical state matters a lot. Gases have the highest entropy because the particles are so free to move around and have so much energy. Solutions are really high energy because they're mixtures. And then would come liquid, pure liquid like pure water or pure ethanol, whatever. And then the smallest entropy would belong to solids. And of course, the type of solid would make some difference. Like a diamond would have extremely low entropy because it's so organized, and whereas a solid like that's maybe like a polymer, like plastic or something like that, would be a little bit more random, a little bit higher in entropy. Here's an example, just to kind of illustrate. Here we've got some salt crystal dissolving in water, so we can imagine the entropy is increasing because those ions are going from being very organized to being a little bit more spread out and mixed together. Two gases can mix as well, and that's going to increase entropy. Whenever the gases are separate, they're more ordered, and then as they combine, mix together, that represents an increase in randomness. Another thing that can happen is if a reaction results in more moles or more molecules than you started with. So here we have 5 molecules on the left, and let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules on the right. So that's going to represent an increase in entropy. This is just an equation form. We have a solid, 1 mole of solid on the left, a mole of gas, 4 moles of liquid, and 1 more mole of solid on the right. So we're increasing not only the number of moles, but we're going from not having a gas on the left to having a gas on the right, and also a liquid on the right. So definitely going to be a positive entropy change, or a positive delta S. Temperature changes entropy. So obviously entropy is going to shoot way up when we go from a solid to a liquid during the melting process, and also when we go from a liquid to a gas during boiling. But it also goes up just as the temperature rises because the particles are moving faster, moving more, they have more energy. So if we're increasing temperature, even if it's staying in the same state, it's going to increase in entropy. So here's an example of what could be a free response question. So the diagram represents the gas phase reaction of NO2 gas to form N2O4 gas at a certain temperature. Based on the diagram, predict the sign of the entropy change for the reaction. So delta S naught of reaction. That little naught, that little degree looking sign there, just means we're at standard temperature, room temperature, and standard pressure. So take a minute to think about this. Pause the video. All right, so hopefully you're going to say here that as we are forming fewer molecules of N2O4, we are decreasing entropy here. So randomness is going down as we group together some of these smaller molecules of NO2 to form N2O4. All right, here's another problem. This actually is what section 9.2 from the AP curriculum is about. It's very simple though, calculating delta S. You're going to be given the values for the standard entropies for the substances, and you just basically have to remember that we have to do products minus reactants. So this is from your formula sheet. The delta S naught of a reaction is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. And so all you have to do is go to the table, make sure you multiply by your coefficients. So these are molar values. So you need to make sure that you want to make sure that you are multiplying the silver chloride, for example, by 2, and also on the other side the silver nitrate by 2. So go ahead and try this. Get out a calculator, do your products added together, so the sum of the products, and then subtract from that the sum of the reactants. All right, and hopefully, so there's my 2 times 96 because my silver chloride was my first reactant, had coefficient of 2, plus 240. I just had 1 calcium nitrate. And those are my 2 products. And then my reactants, which I subtract, I've got 2 silver nitrate at 220 apiece, plus 60 for the calcium chloride. And so if I do that, I should get negative 68, and that would be kilojoules per mole times kelvins. We could cancel the moles because we're multiplying by coefficients, which would have the unit moles. So sometimes you'll see it, I'm sorry, I said kilojoules, it's actually joules per mole times kelvins. But sometimes you'll just see it as joules per Kelvin. All right, and then we also need to talk about Gibbs free energy, which gets the capital G symbol. So this is the energy available to do work, measured in kilojoules usually. It could be measured in joules. You get this equation on your formula sheet. So this is just saying products minus reactants. Not too often, we don't use this one too often. More often we'll see this one, delta G naught equals delta H minus temperature times delta S. Now, the loss of free energy, meaning a negative delta G, means that a reaction is going to be spontaneous, which means thermodynamically favorable, or sometimes you'll see that phrase used. So spontaneous just means that it happens on its own without having to constantly push it along. So, rust forming on a piece of iron that's left outside. That's a spontaneous process. It's not necessarily fast, but it is spontaneous. You don't have to constantly put in work. Whereas if you're, let's say, producing carbon dioxide when baking cookies, getting them to rise, you'll notice as soon as you stop putting in that heat, in other words, if you take them out of the oven early, all of a sudden that rising process stops because that is a non-spontaneous process at room temperature. So unless you are constantly adding heat, you are going to, it's not going to be spontaneous. So if we look at this for a second here, this little table tells us a lot. Anytime you have a process where delta S is positive, so greater than 0, and delta H is negative, both of those conditions are favorable for a reaction to be spontaneous. And that means at all temperatures. So notice temperature, and this would be in kelvins, is part of our equation. And so if I plug in my delta H and it's negative, and then my temperature, if it's in kelvins, has to be positive, and then my delta S, let's say it's positive, well, it would be impossible for me to get anything but a negative answer, right? A negative minus a positive is a negative, right? So it has to be spontaneous, meaning that we have to get a negative delta G. On the other hand, if they're both unfavorable, if we look at this bottom right corner here, If we are decreasing entropy, becoming more ordered and less random, that tends to not be spontaneous. If we are endothermic, meaning delta H is positive, that also tends to be non-spontaneous. And so if we have both of those conditions together in the same reaction, that is a non-spontaneous reaction. Not only that, but there are no temperatures at which that would be spontaneous. And again, if we think about it, it would be impossible for me to get a negative delta G if delta H is a positive number, and then we subtract from that a negative number. The original delta H would only get more positive as we subtract a negative. And so those two are pretty easy to predict. These other two depend on temperature. So if the delta S is positive, so we're increasing randomness, that's good for a spontaneous process. But let's say we also have an endothermic reaction. Well, it could be a spontaneous process. We have reactions that are endothermic that happen spontaneously. It's more rare than exothermic reactions, but they still happen. And so we would say that it depends on the temperature. And when a reaction is endothermic, okay, and has a increase in entropy, it could be spontaneous, but only when temperature is high, because that would give us a large temperature times delta S product. And then if we have an exothermic reaction and entropy is going down, which normally is not favorable for a spontaneous reaction, then that means that it could be spontaneous, but only at lower temperatures. Okay, so let's take a look at an example of a question that you might see. All right, so we have this reaction. We have a negative delta H, so an exothermic reaction. Notice it's very exothermic. It's a large number. So the oxidation of iron is represented by the chemical equation above. I just mentioned this one actually. Which of the following correctly explains whether or not the reaction is thermodynamically favorable? Remember, thermodynamically favorable means spontaneous. Now, it does depend on temperature, and the reason I would say that is because while the delta H is negative, if I look at the expected delta S, even if I don't have an exact number I can plug in, what do you think about delta S here? Is it going to go up or down? Okay, now hopefully you would say that it's going down because we have 7 moles becoming 2 moles. We also have a solid and a gas becoming just a solid. So that represents a decrease in entropy, a decrease in randomness. Okay, so which answer do you think fits best here? Okay, so hopefully A made sense to you. There are more particles, including in the gas state, in the reactants than in the products, so we are actually losing entropy, all right? But because the delta H is large and negative, the reaction will be favorable at lower temperatures. So exothermic reactions that decrease entropy can be spontaneous, but only at lower temperatures.